Here's some of those things, and I apologize, there's only terms on this one, but I got some hydraulic connectivities I'm going to show you in a second with actual numbers on it. But gravels tend to have high porosities and high permeabilities, and unfractured shales tend to be low. So these are just kind of give you some generalities to it. Here, which I apologize for the size of the slide, they only give me so much on an 8.5 by 11 sheet of paper, but here's what's called hydraulic connectivity, which is a term we give to basically how water can move through a system. Okay? And so here you can actually look at silts, and it has from 10 to 0.01 gallons per day per foot squared. Don't worry about the units, because you can change units just like anything. Everyone's got an app for their iPad now that can change all these units in 2 seconds. Okay? In fact, I think these are the same units that people have been using for decades. They just switch them to whatever units they want. Okay? It's not a big deal. Okay? But it gives you a range. Out here we have some really fine stuff that move very slowly. And then over here we have some stuff that move quite rapidly. Here's some tools we've used to look at that. We take our samples and we put them in a shaker and sieve them and weigh them and a bunch of other stuff. That's why I have grad students and undergrads, slaves, to do all this stuff for me. We can run permeameters where we just run water through that soil sample and see how fast it runs through it, and that can give us that value as well. Okay? So what are the rates of groundwater movement, which is kind of what you're getting at. How fast does it move? Okay? It's a great question. It's a question that I'm asked all the time. It's one of the first questions we ask ourselves when we start working on a project. Typically, groundwater moves pretty darn slow. Okay? When you look at the river, does the river have a lot of dirt that has to move through? Yeah. It moves over it, not through it. Well, groundwater has a lot of things it has to move through. Yeah. And so that water molecule has got to go up. It's like going through this crowd. If I wanted to walk through here, there's not much of a straight line. I have to walk all around it. It's more tortuous. So it's going to slow me down. Where if there was a straight shot through there, like the river, with nothing blocking me, I can get through there pretty quick. So groundwater moves orders of magnitude slower than that of surface water. It's still dictated by pressure, no question there. Okay? Generally, a good range would be 10 to 100 centimeters per day, which is, a few inches to several feet per day. Yes, National Geographic did all groundwater people a disfavor by publishing their first version of water. They had a whole journal dedicated to water back in the 90s. They came to the groundwater section. What do they have? A guy standing in a cave with a well sitting there and the water running beneath his feet. This is how groundwater moves. Okay, if I'm in Kentucky, maybe, okay? Not anywhere else, okay? There are not giant underground rivers and giant underground lakes to speak of. Most of the water moves through the dirt and soil, okay? So I've tried to explain that one away at many a talk. Doesn't mean there isn't some there. Yes?
I was going to ask, I have always heard that perchlorate moves quickly through groundwater. So the practical question is it like oil and vinegar that are moving at different speeds or through all these rocks, or is it mixed together?
Good question, and you're going to get a lot more of that. But the simple answer from my standpoint, and I'm not going to go into chemistry with that, is as things mix with the water moves. Not everything in the water moves at the same rate as water. Some constituents, perchlorate, nitrates, tend to move with the water. So if the water is moving a few feet a day, it's going to move a few feet a day. Most things have what's called a retardation factor, and you're going to hear a lot more about those terms. So it moves slower than the water does. And there's a lot of reasons for that. Okay?
Your question is basically what Rebecca's going to be talking about at the next session.
Since I gave him the definitions, I know he's going to talk about it. Yes?
So for the parking lot, and sorry to interrupt you, but for the parking lot, we also put down, because there are people in there here, not just because of Santa Susana. Did we talk about the aquifer system throughout the San Fernando Valley, like the direction of it, and for example, plumes, maybe we could get that addressed at one of the future sessions. Just follow what is put on the parking lot.
When you talk about the parking lot, I was going, did I have to pay to park? I apologize. It's just going, shit, I didn't pay anybody. Okay, that's the parking lot. Okay, good. I'm just glad. Just wanted to check.
I guess for clarification, is that referring to the interaction of the groundwater at Santa Susana with the San Fernando Valley, Simi Valley systems?
Because actually, there's some people here that are actually interested in the groundwater in general, like our drinking water in Los Angeles, and the fact that, for example, we've got a Superfund site down at the eastern end of the valley. We're drawing upon that. Mixed blend water. I'm sure our professor here knows more about it than all of us.
Those I could talk about.
So what I'm saying is parking lots.
But what is the question?
They want more of a general groundwater around the area.
We want to know about the aquifer system and plumes and the groundwater in the San Fernando Valley, because we draw upon that water, as he's pointing out, and you and I, Tom, have discussed it. I'm not trying to take up the time, I just wanted to put it on the parking lot.
Okay.
Okay, so another question. Okay, so going back to it, so how does what's groundwater movement? Well, one of the things we use is what's called Darcy's law. Groundwater has very few laws. That's the good news about it. I don't have to memorize a lot. Okay? And so what it does, it talks about what we call head, or that elevation. So it's over here, it's 100 feet. Down here is at 50 feet. That is the pressure difference that's driving the water moving from one spot to the other. Okay? Now, as it turns out, what we have to do, and here's my equation just to give you some math. Remember the hydraulic conductivity I talked about? That is what this K value is. Okay? So what it is the area for which I'm measuring, the permeability, if you want to call it, the hydraulic conductivity of the soil, how easy does the water move through that soil, times the change in that height, or that pressure head, over the length for which I'm measuring. So here's my length, here's my height difference, and then K would be what's the internal properties of this particular aquifer and how fast it moves. That tells me how much water is moving through that aquifer, and it gives me basically a rate. Okay? Now there's another thing called Darcy velocity, which gives you exactly the feet per day. This is more of a volume. So yeah.
What about with tritium? It becomes the water. Is that like?
We can't hear.
Be more
I'll
denser?
reply it in here in a second. He was asking about tritium, which is a man-made thing associated with our nuclear bomb and atomic bombs that we did in the 50s and 60s, which we use as a tracer. And it does, there again, we use it as a dating tool. We can date the water from when it was, is it 50-year-old water or 60-year-old water? If it's older than that, we can't use that term because that wasn't there. So it allows us to say water was here when that bomb went off. Here's where it is today. How far is that?
But my question is,
Yep.
does it make it heavier or slower?
I'd have to look that one up before I
That's
say anything about
probably
it.
a question for Matt. And it's,
Yeah.
what Dr. Layton doesn't know is that tritium is a contaminant at the site. So,
Really?
so he's talking in general terms. But
Oh,
yeah,
a tracer.
that's something that Matt will address as one of the contaminants and how it behaves.
I have one question for Kay, just to clarify, that is specifically just talking about the permeability of the rock, doesn't take into account the fractures and.
That is what that's taken into consideration, the fractures in the rock.
It does.
The thing which I didn't want to get into is there's two types of, there's intrinsic permeability and hydraulic conductivity. Intrinsic permeability is the permeability strictly of the rock or soil. Hydraulic conductivity is the same as that, but adds on a component that deals with the fluids moving through it. So if it's air moving through it, there's actually a different hydraulic conductivity versus oil versus water. So it adds a little bit of complexity to it, but realistic for this purpose, you think of K as being the properties of the rock, which can be fractures. Fractures have porosity and permeability. So.
That's a constant value, right?
Huh?
That's a constant
That's what your predicted constant volume is, yep. Okay, so when we talk about groundwater movement in temperate areas, we have to worry about the fact that here we get all of our rainfall and moisture during just a few months, right? So water levels tend to go up in November through March because it's when it rains. The rest of the year, they're always going down, okay? Other areas that may be different, and back in the Midwest, they had a lot of thunder showers. In fact, Arizona, for example, gets all of its rainfall in August, right? The monsoons, okay, the rest of the year. So we just have to worry about when that water's coming and going, because that tells us something there again about what's happening beneath us. So we can get wet periods where water table tends to be high, springs might flow, streams may be gaining. During dry periods of time, nice little flower here I finally found, water levels tend to drop, springs dry up, and streams can reverse and actually become losing streams. Okay? So keep that in mind when we're talking about things. So, when I told you earlier There's a, yes?
Isn't there some shifting, and there's some balancing act during the time that the rainfall period ends?
It's not instant. Nothing is instant. So it actually takes time for that water to get down to the ground. So we get all our rainfall. Actually, our peak water levels tend to be July and then drop like a rock after that, or early June in that time frame, depending on where you're at and depending on how much people are using the water. So Central Valley may be slightly different than Mojave versus Orange County.
But wouldn't evaporation tend to pull it back to its surface?
No, actually, once water gets below what's called the depth of termination, then it can't be evaporated anymore. So in certain areas, that can be 5 feet, or once it gets below 20 feet. As it's moving down, you're right, there's always a chance for it to evaporate. But once it gets down to a certain depth, then it's no longer, it may take still days, months, or years to get to the water table, but it's always going to make its way there, which is going to be some of the stuff I'm going to show you here in the Mojave Desert. The other thing to keep in mind is what else is taking water out. It's not just evaporation. Plants, depending on the root system. They're always going to be taking water out and evapotranspirating. They sweat just like we do. So they're going to be putting water back in the atmosphere, and that takes water out. In fact, there's a great study in Montana about a stream that during nighttime it flows. Daytime it doesn't. What's happening?
In the day, it's evaporating.
Nope. Well, it is, but that's not the reason why it's not flowing. Because the plants are taking out all the water and taking out more water than evaporation, lowering the water table. So some of the assumptions we make is how and where the water is coming from. That the water is being recharged through rainfall events or rivers coming in. We have to make some assumptions there, but we can look at the watershed and look at it. That there's return flow. What's return flow? Return flow is I pump water out, use it in the kitchen, put it in the septic field, back in the ground it goes. Or I take it outside, now water my yard. Okay? Part of that water is going to go back into the ground. Part of it's going to go off. Okay? So I have to make some assumptions of what percentage that might be. Then other things we have to look at is pumping, surface water, and evapotranspiration. How do we tell how much the plants are sweating? Basically, we do all the other numbers, and whatever's left, we just claim that as being what the plants are doing. Okay? Hate to tell you, that's basically what we're doing. Okay? Yeah, there's some little things. You can put little bell jars over leaves and see how much is sweating, but yeah, right. The biologists keep claiming that's actually a real number. I haven't quite figured it out yet. So we look at our inputs. There again, we have in equals out plus or minus change in storage. So in, precipitation, some of that return flow. We have some springs and streams coming in there, and we have groundwater. Our outputs can be pumping, evapotranspiration, overland flow, and groundwater as well. So we have groundwater flowing into our bathtub and leaving our bathtub. So we have to calculate for both those. So here, out in the Mojave Desert, there's a basin called Este, which means East Basin, which is Lucerne Valley. So if you go, you come out of Big Bear and you come down the north side of the mountains there, you're going to go right into Lucerne Valley. This data is actually for that valley. And it's a study some students and I did. So we went and calculated the inputs, the outputs, and looked at the totals. So now you don't have to worry about these numbers, but here's 3 different reports. And look at these numbers down here. What's the negative sign mean? Yeah, that means they're using more water than's going in there naturally. Okay, now if I'm a citizen out there, is that good? Probably not. My well is going to go dry. I may run out of water completely. Okay? Those are bad things. And so when they looked at these numbers, they went, holy cow, we're going to have to do something. Okay? So one of the things we have to look at is sustainable yield. Okay? And I apologize, I didn't use the quote out of your book, but I'd use Fetter instead. The amount of naturally occurring groundwater that can be economically and legally withdrawn from an aquifer on a sustained basis without impairing all the different things out there. Okay, so we want to be sustainable. We want to make sure we're pulling out and utilizing our resource in a manageable way. Obviously, with those negative numbers, Lucerne Valley was not. What happened is they adjudicated the basin. Okay, so we're going to see what happened before they did the legal adjudication and what happened afterwards. Here is a common well. Starting in the 1960s, water levels are going straight down. That's those negative numbers. Okay? Then adjudication hit. Poof. Everything became flat. Okay? Flat is good. Okay? The problem they have is this flat area here is, what is that, 50 to 100 feet below where it started. Okay? So they've lost storage out of that basin. Okay? But it shows there again how we're trying to manage the thing. So some assumptions we had to make is long-term monitoring. We only had a few wells that had that long-term data. Data is key to groundwater studies. The more data you have, the better off you are, okay? Because things can change. Frequency of monitoring. This is a big deal. Do I go out there and take a water level today and a year from now take it? Okay, what did I miss? Yeah, I have 2 data points. Great. I can draw a straight line between 2 data points. Okay? 3 data points, I can actually maybe see a trend. 4 is even better. But what I missed was that seasonal changes on the water table. As we just talked about, things go up and down seasonally. It's nice to know what that's happening. Okay? Some cases you need daily or monthly or yearly, sometimes hourly. I have a data station in Malibu. I'm looking at tides. I want 6-minute data because I want to see what the tide's doing every 6 minutes. Okay? Now, you can get data overload real quick, so it's something you have to consider too. And Excel can only handle so many data points, regardless of what Microsoft tells you. Okay? So here's a series of wells out there, and you'll notice here all of them are all going down until this point, and at that point in time, they begun to go flat. And here's what they look like today. Okay? So they have become sustainable out there. They're using exactly the amount of water that's going into the basin. That's the story to be told here. Okay? The problem is what they need to be doing is using less water than's coming in so they can refill that basin. Now, every time there's a problem, there's an opportunity. Okay? One of the things that LA, Orange County, and San Bernardino are looking for are places to store water during wet periods when we don't use all the water so we can keep it for those times when we need it. Well, here is 150 foot worth of aquifer that used to be wet that's ideal for putting water in. Yes? What about some science? They did have some out there, and I'll show you some pictures. Not from here, but they had a little bit because they went down. They had some cracks in the surface. It wasn't as bad as the Central Valley. However, with the science, you can have rebound. Orange County, according to the USGS, breeze goes up and down seasonally.
That graphic doesn't take that into consideration.
Yeah, it does, because it's based on the top of the well. The well didn't move. Ground might have, but the well didn't move. And we're only talking about a few inches. The land subsided out there less than a few inches. We're talking hundreds of feet. Yep, good question, though. I appreciate that. So anyway, so here's an opportunity. And so the Mojave Water Agency is actually looking at putting recharge water out there. They actually have a pipeline in the, which canal is that one? The Los Angeles Aqueduct, Mojave Aqueduct, California Aqueduct goes by there, yeah. So they're actually looking at purchasing water, storing it there, because there was water there before, so, and it was obviously easily retrievable because they pumped the heck out of it before. So there again, for every time there's a problem, there's always an opportunity. So one of the things we look at is those hydrographs, and we really want to look at decline in water levels, increase of them, and change. It's really a balancing act. And there again, this is something that water agencies around California use all the time. They're trying to play this game, okay? Trying to keep things within balance. So how does groundwater flow to a well? Okay? What is a well? How many people in here know what a well is? Okay? So is the earth. Hole in the ground, okay? It's a hole in the ground. Typically a well, be it a monitoring well, production well, everything else, is a piece of pipe in the ground which has slots in it or holes in it that allow water to come from the system or geology around it into here and allow you to easily pull it to the surface. Okay, so that's what this is. It's just a sample I have. Anybody wants to look at, they're more than welcome to. But it's really just a screen. They can be made in all kinds of different things, stainless steel, PVC, black pipe, whatever. Okay? So it's a piece of pipe in the ground, allows water to come into it. So what happens is, here's my screen. Here's a nice little picture I stole from one of the screen manufacturers. Water moves into it. It does not move into this solid piece of pipe. As it moves into it, it creates what's called a cone of depression. Think of an ice cream or a snow cone. Okay, those little cones. The water is pulling the bottom. All the water radiates towards it in a circle to that point. Why does it go there? We lower the pressure in the well by lowering the water there. Water wants to move from high pressure to low pressure, then back out of the ground. Okay? So that's basically the principles of that. With that said, it can only come in at these zones. Okay? Now, are there open wells? Yes. Where we just drill into bedrock and leave it wide open? Absolutely. Water comes through the fractures that have been intersected by that hole and then come up. So it doesn't always have to have a screen. Yes?
You need to mention that coning would be only if you're pumping it out. Otherwise,
Yes, absolutely. It's a good point. Very good point. Sorry about that. Yeah, the cone is only there if you're pumping. If you're not pumping, it's just going to be showing you where the water table is at, if you're an unconfined aquifer, or the potential metric surface like we saw in my little diagram earlier. Why are groundwater pumped? We have private municipal well supplies, irrigation, and industrial. You can see here where water is being pumped, and yet water still continues on down here to the river system. We can sustain ourselves even next to river systems if we do it properly. Here's that cone of depression while pumping. Here's where the water table would have been without pumping, or would be if we turn the pump off, and then water is migrating down here. So this actually gives you an idea how water is pulled in. When we sample a well, the same thing happens. We're pulling water into our well from the surrounding geology so that we can get a good chemistry sample or a good flow sample or whatever it is we're looking for. Yeah, we can skip that one. Man's interaction, obviously we pull a lot of stuff out. We have pollutants, which are obviously a concern here tonight. We can have fissures. This one here is from Lucerne Valley. It's about 2 feet deep. The fracture was. Land subsidence was only a couple inches. Okay. Here is the famous picture from the Central Valley with the guy standing next to a telephone pole. That's what the ground surface was in 1925. That's what it was in 1955, and this is what it is in 1977. The whole valley's been sinking. Okay. Now, it's not all due to groundwater withdrawal. Some of it's oil and gas, but the whole land surface has been shrinking downward. What's that? It is very amazing. This is a famous picture, and I've stolen it many a time. So I'm a professor. I'm allowed to steal. I'm given a free license to steal images anywhere I can. Okay, so water quality. Okay, and this is very general. Okay? Water quality is comprised of pure H2O with additives in it. Okay? Now, pure H2O, distilled water. You can buy it at the grocery store. Is it good for you? Why not? It will demineralize your body. Okay? We need those minerals to be human beings. Remember, that's a little pile of stuff we had there with Star Trek. Okay? When water moves to the rocks, it interacts with those rocks and soils and picks up minerals. That's good for us. Okay? Now, why are things chlorinated? That's a different topic, but I keep arguing with my wife. In fact, I like we're on city water and it's chlorinated because I don't have any bugs in the water. Okay? She claims it's all bad tasting. Okay? Well, I've had some really clean water that was horrible tasting. Just go to Ohio. Okay? Hydrogen sulfides in all the water there. Okay? It's not going to hurt you, but it tastes like, rotten eggs. Okay? So, one of the things we have to look at is what are some of the sources of water quality degradation, or how is it being impacted? Now, in the Mojave Desert, one of the things we deal with is arsenic and hexavalent chromium. Okay, Hinckley. We've all seen Aaron Brockovich. Okay? I've been working out there. Okay? Obviously, we have a lot of water quality over about a 5,000 square mile area in multiple basins. There is some naturally occurring hexavalent chromium and arsenic in the area. And in fact, in some places, the naturally occurring degradation of those rocks there, the granites, are producing water quality which would be bad for us. Okay? It isn't always man. Okay? However, we do enhance things in different places. Okay? Perchlorate is something we import, right, from Henderson, Nevada. Okay? We bring it in. It's not bad enough we can pollute our own cells. We got to bring in some other ones stuff. Okay? So there are issues. Nitrates are another one. Okay? Nitrates are man-made. They start at the surface and they work their way into the groundwater. Okay? That's I think the blue, is that the blue baby syndrome? I don't really remember. It's farms, fertilizer, but septic tanks. Okay? We used to have phosphates and other things. So all that stuff can impact. And certainly as that stuff goes into different soils, sometimes the soil cleans it up. Okay? Oil and gas, gasoline. There's bugs that eat gasoline in every soil on Earth. Okay? They all exist everywhere. They're laid dormant until such time they get enough food, which in this case would be gasoline, and they start eating it. Okay? Is that always the case? Sometimes the pollutant is too great for them. Just like us, right? Too much sugar is not good for us. Okay? A little bit of sugar is great for us. Okay? Same thing happens with a bug. So sometimes we can get too much. It may not be the right type for that particular one, but we're learning a lot more about this stuff. It's not, I mean, groundwater is a young science. That's what makes it fun. I keep telling my students. I mean, I'm already done with my research. I mean, my big findings, whatever the heck they were, they're done. The next generation, you guys have a whole field in front of you. We're talking about a science that's only been around for a handful of years. Okay? So we're just learning a lot of this stuff, and so it's still something to be done there. But certainly see lots of interaction with these different rocks can produce different types of water. Okay? Acid rain will eat limestone, dissolves it. That's why we get sinkholes and karst topography. Okay? Other areas, that may be remineralizing stuff that's good for you. Yes?
Are you going to touch on any vapor intrusion from these aquifers?
No, but I can. Here in this slide, but probably not. No? Okay. Okay, I'll shut up. Damn, how much time we have here? Are we on time? Everyone excited still? Okay, start telling jokes. Okay, here's my usual picture for a gasoline station. Every corner in America used to have 4 gasoline stations. Unocal on one side, Chevron on the other one, Exxon on the other one. They all end up suing each other because all their plumes mingled and everything. Great, okay, it's good work for the environmental business. Okay? But nonetheless, we have a whole bunch of wells we put in and they all leaked and stuff. And then they got MTB in there because the state mandated we had to have it. Great for air pollution. My mother grew up in Burbank, I don't know, long time ago. Okay? She said she lived in Burbank, couldn't even see the mountains. Okay? Any day of the week, could never see the mountains. Well, today we can. Okay? Yeah, there's smog and this is tines, but it's a lot. Our air pollution is much better because of it. Okay? Unfortunately, it didn't do a great deal, for our groundwater sources, except provide a lot of jobs. Okay? And in some cases, it might have, caused some other things. So it's not good, but there again, it's something that's happened. So certainly landfills, dumps, septic tanks, people dumping things on the ground, all of that can get into our ground. One of the things I bring up to my students is like the ocean. The ocean is the ultimate toilet. Anything and everything that's been on the land surface is in the ocean at some part. Okay? Same with our groundwater, it's becoming, okay? We're starting to sample for pharmaceuticals and all this other stuff. And we can sample now for levels that were undreamable a few years ago, thanks to computers and analytical capabilities. The stuff I'm doing in Orange County, I monitor the Orange County Recycle Program, where they recycle 100 million gallons a day. We monitor some of that stuff into 0.00 parts per trillion. So I don't even know what that's called. Okay, now, whether or not it's even real, I'm still questioning, but that's what UNLV is working on. So there are some levels that are just phenomenal. Whether or not that makes it bad for us, I don't know, but we can sample it. Okay? So those are things we have to keep in mind as well. Obviously, landfills, agriculture has done a lot of stuff, waste lagoons, all that stuff has had impact on our water quality. So, what are the tools that we can use? Yes?
I was going to ask if there's going to be at some point a characterization of the groundwater in the San Fernando Valley and Simi Valley, in other words, the lands around the field lab as well as at the field lab. If that's being done or has been done.
If it isn't being done, I will write a grant and you guys can fund it. That'd keep me busy for a while. Yeah.
That's exactly what I was asking to put on the parking lot. I'd like you to do it, and Watermaster, you could put that on the parking lot because that's what I'm talking about too. We all want to understand the impact. For example, we have the Chatsworth Reservoir and Chatsworth Nature Preserve. When you're talking about places to store water, that was a place that we did store water, and we aren't anymore. And that's why I'm saying put it over on the parking lot.
We're having a number of, I think the lecture series that are going to be coming up are going to talk about the investigation at the sites, strategies for those kind of investigations. That will be in later lectures, and that's a discussion that you can have with DTSC when we start talking about the groundwater RI report, talking about the investigation.
But Diana, I think it was to ask the question, and I are saying that in over here, people like us, we're looking at the groundwater in general, the impact from San
Yeah.
I already have written down aquifer system in the San Fernando Valley, but I think we've broadened it. I hear that you've broadened it. What I'm not sure of is whether this lecture series of 6 presentations is going to be able to answer that, because we've got an awful lot of stuff already on the list of things that are going to get presented.
Well, let's just say that could be a future thing. By that time he has his grant, you know.
It's going to be years of studying, years. I got to retire here, so I'm going to pay for my young kids to get through school someday. You know, it's back like that. We study everything to death.
Maybe I should just say that I understand what you're saying. In regards to the investigation on the site, if that leads us into, that investigation will extend out to the extent that Santa Susana has impacted not only the site conditions, but the off-site conditions. So if that includes San Fernando Valley's aquifer and Simi Valley's aquifer, it will extend out to that extent.
Your investigation.
The investigation.
Yeah.
Is that?
And all your kids will be through college by the time we're done with that discussion, right?
I have a 6-year-old, so.
Okay, I would like to try to let Dr. Lanton finish his presentation.
Okay, one last little bit here. So what are some of the tools we use for investigating something we can't see? Okay? You've seen some of the data sets I've used and some of the things we're talking about all the time, but how in the heck do we actually do it? Well, one of the things we actually start off with is remote sensing. And you can see a little landside imagery up here. We actually use some satellite imagery, aerial photography, anything like that that we can see, even from space, can tell us something about the rocks, which give us some idea of maybe potentially the properties of those rocks. And in some cases, it certainly allows us to tell us where the rivers and lakes are, and actually can give us some heat difference. We look at infrared. Maybe we can see if the river is gaining or losing. Okay, so there are things like that we can use from a remote sensing standpoint. We actually use what's called geophysics, okay? All kinds of different things. You've heard seismic, the oil guys use. Well, we use the same thing for groundwater. We use things like ground penetrating radar to look at things. Same radar they look at planes at. Someone got the clever idea, well, why don't we put it on the ground and see what it looks like there? Okay? It works pretty nicely. Very shallow, but it allows you to look at things. We look at the electromagnetic properties of things or the resistance of things. So there's all kinds of different tools in our toolbox, and groundwater people are, what I like about it is I'm a jack of nothing, but I know about everything, okay? Because I have to know a little bit about remote sensing, which is really cool, a little bit about geophysics. I need to know something about how to put wells in, how to design a well, how deep do I put it in order to investigate this particular problem, how big do I make it? Do I make it 12 inches in diameter or 2 inches in diameter? Depends on some of the tools I may put down. So you have to know a little bit of everything. Yes?
Yeah, as part of the code regulations, I think the Water Quality Control Board requires tracer studies of groundwater systems.
Not that I'm aware of.
Yeah.
I've done some tracer studies, but they're not required.
To use for groundwater replenishment.
Oh.
Groundwater replenishment. They require tracer studies. Could you comment on what kind of tracers might be used in that kind of situation?
Let's ask
Repeat
about
the
tracer
question.
studies
Yeah,
for
just-
groundwater replenishment. And a lot of times they're using isotopes, but tritium may be part of that too. Places like Texas and down in that area, they'll actually use rhodium B dye, which is a dye they put in there, somewhere where I'm going to use today. Watch it rush out. They just go downstream and sample at different wells and see when it pops up. But they got things moving fast there because of karst. But tracers are just basically elements that you can put in the water or things that are already in the water that allow us to track where water's going and give it a rate to it. But also modeling is another part of that. So you can do computer models, such as this one here, based upon all the information we go out there and collect. You throw it into a computer, you run some known algorithms that have been checked and verified and understand the principles of groundwater, and actually see in 3 dimensions where water's moving, how it's interacting, and what's going on. Remembering it's an average of the whole system. It's not necessarily going to give you that spot. It's exactly this concentration. Yeah?
You mentioned karst a second time. Karst topography is in Kentucky. Is there any in Orange County? You just now mentioned Orange
Nothing in Orange County.
in Southern California.
There's not what I would consider karst topography. No. Okay, is there some limestone and stuff? Yeah, but we don't get enough rainfall to do some of the things it's talking about. So we don't. The sinkholes we see on the TV are because pipes burst and eroded things out. It's not because of Florida where everything got eaten away and now there's a big hole down there. In fact, I was talking to a driller the other day. I lost a $1 million drill rig because it fell in a hole. Uninsured, by the way. He's out of business.
John, did you have a question? Yeah. Oh, I thought you did. I'm
No,
sorry.
not
Okay.
yet. But if you have one, I'll answer it. Okay, okay. No problem. Other ones we look at is we do what's called an aquifer test. We pump water out of a well and we monitor what's happening around it in different monitoring wells. From that, we can get an idea of what the aquifer as a whole might be doing in that area. That gives us a better idea of the hydraulic connectivity of the particular material. It also gives us another term we use, which is transmissivity, which is another term very similar to hydraulic connectivity. It takes the thickness of the aquifer times hydraulic connectivity. So it's T equals Ka. We also use water chemistry, such as these down here. And we do some geology models, some geophysics or borehole stuff, aquifer testing. These are my students doing some stuff here out on the beach. But you can also put all this into a model. So we have a whole set of tools in our toolbox to try to attack any one problem. What that said is not every tool is needed for every single problem, obviously. Okay? But they're all there, and they usually are pretty well pick and choose based upon the conditions and the desires for what we're looking for at those particular sites. So I've been on sites like Mojave Desert where we use everything. I got 5,000 square miles. So we have to use remote sensing to narrow in things. We go out and we do geophysics, and we drill wells, and do aquifer tests. So we're utilizing every tool in our toolbox. Okay? Most big contaminated sites will use every tool in the toolbox. Those small gasoline stations might not be able to have the money for it, and it may not be appropriate. Okay? So there again, the scale of the problem, scale of the project, think of your tools as being there at your availability as need be. So with that, obviously we've covered all this stuff. There's a nice picture of me up by Mono Lake in that area. One of my pictures in Mojave when we drilled 24/7. So at 4 o'clock in the morning, it was a nice little sunrise.